Hello. So in this video, I am going to present a couple of theorems. They are not in the book that we're using, at least at the time that I'm recording this, but nonetheless they're sort of hinted at throughout the book. I figured I would just go ahead and present and prove them for you guys myself. So these are just a couple quick sort of boundedness theorems. So the first one, which you can tell from the huge amount of space I left to prove it, this one is pretty short. So this claims, all right, if you have fn from R to R and it's a uniformly bounded sequence of functions, then in fact fn is also pointwise bounded. And this should be sort of intuitively clear, but just to sort of formalize it. So since the fn's are uniformly bounded, remember what that means. There is k in R such that the absolute value of fn of x is less than or equal, let's say, to k for all x in the domain, which in this case is R. In the domain, because I didn't specify some sub interval that it's uniformly bounded on. I'm just saying they're uniformly bounded, and that means on all of its domain. So since it's uniformly bounded, by definition, that tells me there's some constant function, there's some constant value such that fn is less than or equal to k for all x, and I didn't write it, but clearly for all n as well, right? So the whole point of uniform boundedness is there's one constant to rule them all, right? It works for everything. But the thing is I can think of a constant as a function, right? The constant function. So let m of x, the pointwise bounded function, the pointwise bounding function, be the constant function k, and fix n in n arbitrarily. N in n arbitrarily, and x in R arbitrarily. Thus, fn of x is, again, less than or equal to k, which is m of x. But this is true for arbitrary n as well as x. So clearly then, since this is, right, if I take a limit of n on both sides, doesn't change this, doesn't change that, I get the limit of fn is less than or equal to m of x. So the sequence fn is pointwise bounded. So this is just, I mean, again, this should be really sort of so obvious to the point where it might even be hard to prove because you're not really sure what to write, which is one of the reasons I did this. But it should be very, very obvious that this is true because I already have a number that is a bound and I'm looking for a function that is a bound. So I can just use the constant function that is that number and I'm all set, okay? So that one, not terribly thrilling. This one's a little more interesting. So this one says, okay, so the second one here says that if we let fn from some closed interval ab to r, and we suppose that each of these fn's is continuous, fn converges to f uniformly, so the sequence converges to something, converges uniformly, my claim then is that the entire sequence fn is uniformly bounded by necessity. Now this is interesting because I've made no claims about boundedness anywhere on here until my conclusion, right? I didn't claim that the fn's are bounded. I didn't claim that f was bounded, so maybe f itself is forcing a bound or something like that. The claim is just that the fn's are continuous and it converges uniformly to f, and thus it has to be uniformly bounded, okay? So let's go ahead and prove that. So since fn is continuous for each n. And Fn converges to F uniformly. We have, so I'm going to record a number of observations here, just sort of all at once as a list. So first and foremost, the one that you probably are thinking of off the top of your head because we've been doing this part of it, Fn converges to F uniformly, Fn is continuous, this tells me that F itself is continuous. Right? But since A to B is a closed interval, so remember all these things are being defined on a closed interval A to B, and that is not a mistake. In fact, that is absolutely necessary for this to work. So since these things are being defined on a closed interval by the extreme value theorem, I have that, so Fn's are on the closed interval, but F is also continuous on the closed interval. So the extreme value theorem applies to all the Fn's and the F's. So by I guess, part A, because that's how I've written it at this point. So part A for each n, Fn is bounded uniformly. I write uniformly in the sense that Fn, the single thing, right, for each n, fixing n, each Fn is bounded by one value, is bounded by some Kn in the real numbers. So I'm not claiming that the uniform part of this means that the K here is bounding all of the Fn's. I'm saying for each n, I have a uniform bound, meaning for any x, the Fn of x for that particular n is less than this particular bound. And that's not quite what I want to get to, because to have a uniform bound, I need that I have just one k to rule them all, right? I need this, this one k in R. Right now I have a sequence of k's, these kn's, okay? And, moreover, again, since Fn is continuous, that gave me that, but F is also continuous on the closed interval. So there exists some k0, which is okay to write because I'm starting from 1 to infinity, so I only have k1 through infinity. Here I have k0. So that F of x is less than k0 for each, well, I shouldn't say for each, I guess, for all x and r. And again, to be clear, this k0 is also an r. I'm sure that was clear by context, but just to be formal. So since I have a closed interval, I get the extreme value theorem telling me all the Fn's are individually bounded. And so I'm giving each Fn its own Kn, and that Kn is the bound on that Fn. That starts at 1 to infinity, so I tacked on a K0 for the thing that I converge to uniformly. That's the bound there. And so I have this sort of sequence now of bounds, and I want one bound to rule them all, right? The last thing I'm going to note, getting back to this part here, Fn converges to F uniformly. So there exists, so this is not having to do with the extreme value theorem, I'm just going to use this part here. There exists n so that if n is bigger than n, then fn of x minus f of x. So what I'm doing here is I'm using the definition of fn converges to f uniformly. That tells me that for any epsilon greater than 0, there exists some capital N, so that if I pick something bigger, I'm less than epsilon. But I'm just going to fix an epsilon. I'm not going to introduce epsilon as a letter. So I'm just going to say this is less than, say, 1 for all x and r. Right, so here my epsilon that I would use is 1. Okay? All right. So I've recorded all these things that are just consequences immediately of my original hypotheses, along with in this case, the extreme value theorem. Now, I'm going to use something on here for just a little bit. So recall, so this is something you should have encountered already, but if you don't, I'm going to recall it here for you. Recall the reverse triangle inequality. So what this says, the reverse triangle inequality, says that if you have a plus or minus, doesn't matter, plus or minus b, that this thing as a thing is greater than or equal to the absolute value of a minus the absolute value of b, close. Which in particular is then greater than or equal to whichever way you want to write this without the absolute value. So a minus b or b minus a. Okay. So this is just one of those analysis facts that you should have done way back when. But in case you haven't seen it, because sometimes things slip by, I'm just recording this as a fact. I'm not going to prove it. So I'm going to switch colors and do a different section of the board here. Okay. So I have all these facts. Okay. So by number 3, and number 2, part B. So here, I'm going to use the reverse triangle inequality to say that this thing is bigger than, and I'm going to split this apart with a negative inside. So in particular, I'm going to have that fn minus f is less than, this is less than 1. Right, so that's the reverse triangle inequality I'm doing. In the case of how I wrote it, I'm doing this is less than, this is less than 1. Okay? But I also know that f is a bounded thing. So if I take off something even bigger for f, right, so I'm subtracting it off. So if I subtract something even bigger, my overall thing is going to get smaller. So in fact, I have that this thing is bigger still. I guess I should have written it a little further to the side. I'm going to have, yeah, that's what I wanted. I'm going to have fn minus k naught. So in particular, that is to say here that fn is less than 1 plus k naught for all n bigger than whatever that capital N I fixed back here was, here. Okay? Okay. So I'm almost done, believe it or not. I'm getting close. So now, let k, which I'm going to claim as my uniform bound, be the max of, so I want to take a max of a, so you should always do maxes of sets. And in particular, you can't guarantee that you have a maximum in an infinite set. You might, but you might not. So it is always good principle, if you can, to either only write finite sets when you have a max, or if you have to have some sort of infinite thing, you have to show that a max exists, that it actually does, one of those elements really is the maximum, okay? Here I'm gonna have a finite set. So I'm gonna have the max of kn such that 1 is less than or equal to n is less than or equal to capital N, union, and then this thing, 1 plus k naught. Okay, so here I have n items plus one more. N plus 1 is a finite number because capital N is fixed. So k as a maximum, well-defined, life is good. So I'm going to claim k is a uniform bound of the fn's. Okay, so to do that, I'm going to essentially show that for any n, k is still a bound for all x's of that fn, okay? So I'm going to prove this subclaim by fixing n in n arbitrarily. This is sort of like fixing the epsilon greater than 0. I'm going to show it as an arbitrary thing so it's working, so it works for all n in n. So case 1, n is less than or equal to n, right? Then fn of x, this thing is less than or equal to kn, because that's what the definition of the kn's were, right, over here. But kn is a member of the set because it's less than or equal to n. It's a member of this set. So whatever k I picked, it is a maximum of that set. So this has to be greater than or equal to k for all x, to be clear. Right? So basically, if I picked one that was less than or equal to n, it was already in this set. And since it was already in this set, and I picked the maximum of that set, I have something big enough. On the other hand, case 2, if n is greater than capital N, then, well, I still want to know something about fn of x, an absolute value. But remember, that was what I did up here. Fn is less than 1 plus, so this is less than 1 plus k naught for all those n's that are bigger, right? So this one's bigger, so that's true. And this was true for all x, right? So I guess I'm looking back at this now and I realized I didn't write of x, which I should have, as that's how I've been writing it. This is the standard sort of industry standard way of writing when you're doing a uniform bound. You do it without the x, just like we do that with the convergence, right? Writing it without x is saying that you're doing some sort of uniform thing. So this, by writing it this way, that's the sort of conventional way of claiming that this is a uniform bound, which is why I just did it completely on autopilot. So it's not wrong to write this, but to be clear, this was true for of x, right? There was of x everywhere there. So this is less than that for every x, but that is, again, one of the elements of my set, so k can only be bigger than that. And again, also for all x. Since cases 1 and 2 are exhaustive, so this is the way of saying those are the only possibilities. Either it's less than or equal to n, or it's greater than n. There's no other options, right? We conclude fn of x is less than or equal to k for all x in R. Thus, the set fn, as n goes from 1 to infinity, is indeed uniformly bounded. Okay, so this is a classic approach, which is one of the reasons I wanted to prove this. Because if we step back for a minute, and feel free to rewind and rewatch this video to go step through step with this sort of insight or this thought in your head. If we step back for a minute, there are sort of two fundamental issues at play when you're trying to come up with a uniform bound. There's the issue of coming up with a bound that works sort of at a function, an individual function level. So claiming that an individual fn itself is bounded. Because it could be that an individual fn itself isn't bounded, so there's no way you could find a uniform bound, right? So I got through that problem by doing these kn's, which is typically how that happens, is that you can come up with a bound that works for an individual function or some finite collection of them. And that gives way to the second hurdle that we have to get through, which is that even if we come up with a bound for each individual function, that still gives us a sequence of bounds, and we want one bound that works. And just like we said that you can't take a max of an infinite set and know that you have a maximum, you can't just say take the max of kn's, because it could be that kn equals n, in which case it has no maximum, right? Because as n goes to infinity, kn goes to infinity. Each individual kn is bounded, but the sequence as a whole might not have a maximum, right? And so this technique, this approach that I've shown here is sort of the classic way around that, which is that I sort of push out far enough down the sequence of bounds that I get some sort of tail behavior, meaning that I get something where all the bounds, as I get sort of close enough down the way, are all close together. In some sense, there's some reason to believe that these kn's maybe don't converge, but they sort of have that sort of behavior. They all sort of hover near a value, right? They may oscillate every once in a while far enough away that it doesn't actually converge, but they're near something. And importantly, what I really care about is that they're bounded, so I can pick something that is bigger than the tail's sort of oscillation, right? If I think of the kn values as some graph, even if I'm sort of eventually just doing this and it never actually stabilizes enough to be convergent, I can still pick something big enough that gets past the tail. And that's the part I care about. Because even if I have, so as another example, I realize I'm writing like right in the middle of my proof here, but even if I have some wild behavior at the beginning and then it sort of flattens out, if I can curb this tail by a uniform bound, right? I find some here k naught value that's bigger than all of the k's eventually, then I only have finitely many previous values that I need to worry about some sort of maximum for. And now I have 1, 2, 3, 4 values to take a max from. It's finite and I'm all set. That's exactly what happened here, okay? So this idea of coming up with a uniform bound of functions often comes down to this idea of trying to find bounds for each function, or some like nice way of looking at the functions that you sort of group them, but you usually end up with a whole lot of bounds that way. And then you need to find out if you can sort of collect infinitely, all but sort of finitely many of those bounds in some way, like this tail technique, so that you can get one bound on all of those, and then you just have a few, finitely many left over that you can max across and get the bound that actually works, like we did here. Okay. So with that, those are the two theorems, the one that was sort of very straightforward and easy, the one that was arguably less so, and we're all set. So there we go.